Okay, good morning and welcome to the 2025 DIS workshop in Cape Town, South Africa. It's a pleasure to be here, and it's my pleasure to present the 2025 Guido Altarelli Award. Let me start by saying thank you to our sponsors, Springer EPJ, World Scientific, and the Fermi Center. So we appreciate their support, and this award would not be possible without their generous contributions. So the Guido Altarelli Award honors the memory of Professor Altarelli, who was one of the founding fathers of QCD, an outstanding communicator of particle physics, and a mentor of strong supporter of junior scientists. And so it's very appropriate that this award is recognizing junior scientists in our field. So it's a pleasure. Let me start with a bit of history. And Professor Altarelli was a member of the first International Advisory Council for the DIS workshop and helped it start up. And you can see the list there, a very distinguished list of folks. And the DIS conference has been going on for over 30 years now. And I think it's one of the top conferences that really matches the experimental results with the theoretical predictions. And that's how we make progress. And over the years, we've had some fantastic advances through this, and so it's a real pleasure to be part of this. And this is the legacy of Professor Altarelli and the others that made this happen. So that's some history from my point of view, but we'll also have some firsthand history. In a moment, you'll hear from Professor Yuri Dokshitzer, who will give you some personal reminiscences with Professor Altarelli. And of course, you recognize both Dokshitzer and Altarelli are the D and the A in the well-known D-Glap equations. And Professor Dokshitzer is also the editor and co-author of the Basics of QCD, and he's a visionary pioneer responsible for numerous groundbreaking ideas that have reshaped our field. So it's a great pleasure to have him with us today, and he'll make a few comments in just a moment. But let me go on and note that this is the 10th year that we've given the Altarelli Prize. And here are the lists of the previous winners, both the theory and experimental winner, and that's a very distinguished list of folks. And they've, even after they've got the prize, they've gone on to do some very, very impressive things. So that's a distinguished list to be part of. And I think our awardees today will, again, also match up to that. So again, I thank our sponsors, Springer EPJ, the Fermi Center, and World Scientific. Also, let me say thank you to all those who have nominated candidates. We had a pool of over 20 applications, very impressive pool, and that made for some very difficult deliberations. And so let me also thank my selection committee that helped us work through this process and come up with the final selection. So again, thank you to all of you. So without further ado, let me announce the first awardee for experimental category is Miguel Arratia, and he got his PhD from the University of Cambridge and did a postdoc at the University of California, Berkeley, and is now at the University of California, Riverside, where he recently won a US DOE Early Career Award. And so it's our pleasure to recognize him for advancing jet studies in deep inelastic scattering and developing high granularity calorimetry for the electron collider. So congratulations to Miguel. Moving on to the theoretical award, it's our pleasure to recognize Rene Poncelet, who got his PhD from Aachen University and did a postdoc at Cambridge University, and is now an assistant professor at the Institute of Nuclear Physics in Krakow, Poland. And so it's our pleasure to recognize him for outstanding contributions to precision calculations of the top quark and Higgs boson, which have profoundly influenced LHC analyses. So again, congratulations both to Rene and Miguel, and we're very pleased to present you with this award. So without further ado, we will move on to some comments by Professor Dokshitzer, and then we will follow that with the brief research presentations by Miguel Arratia and then Rene Poncelet. So thank you, and I will turn the floor over to Professor Dokshitzer. Thank you.
It's an honor and a pleasure. So, fortunately, in this audience, there is no need to stress the role of deep inelastic scattering as one of the pillars of the modern particle physics. And apart from historical place deep inelastic has in our field, which everyone knows, and it's what you teach young people, there is another aspect which is a little bit more difficult to quantify, but which, in my opinion, is not less important, if not more. This is how deep inelastic actually changed our view upon the hadron physics. So first of all, deep inelastic, its appearance, the insistence of Bjorken to measure inelastic instead of elastic electron scattering at SLAC was a sign of awakening of quantum field theory. And this happened importantly before anything else, before weak interactions, before obviously QCD, and even before discovery of quark, fourth quark, which actually put a final exclamation mark on our belief in these strange objects. So a lot of interesting keywords have appeared immediately in relation with the deep inelastic phenomena, such as duality, the word precursors, which was there for many years as a big puzzle. And the word duality has developed in a pretty strong manner since early days of deep inelastic, starting from Bloom-Gilman duality, as Michelangelo mentioned, some rules which you would use to smear the resonance behavior into the smooth partner model predicted behavior, all the way to a real detailed, if you wish, microscopic duality, where people are trying to look at production of hadrons by starting production of quarks and gluons, literally. In certain sense, deep inelastic turned completely our take on confinement. Thanks to deep inelastic, we know that proton is actually fragile. There is no strong forces in strong interactions. Actually, proton exists not because it is so tightly bound state where quarks are not allowed to fly away, but instead just by chance, because it happens to be the ground state of a three-quark system. And as a result, as I mentioned already, result of this understanding, it turned to understanding of appreciation of the fact that confinement actually is not doesn't consist on pulling quarks back together by some strong forces, but instead of gentle transformation from colored degrees of freedom into colorless hadrons. So, just to wave a flag that the story of deep inelastic is far from being over. There are still challenging questions around. Let me mention just two of them, which of which deserve a special lecture, which I certainly won't bother you with. First of all, there exists an intricate relation between space and time-like development of Parton cascades. That is, Parton distribution functions versus a structure of jets. Or in other words, structure functions of deep inelastic versus fermentation functions of a plus or minus annihilation. And understanding of this relation helps you to understand how come that the one and the same partner Hamiltonian, so to say, the famous splitting functions, they lead to so different, drastically different structure of final states. When you compare space-time evolution, which is deep inelastic, with time-like evolution, which is jet development. And the second subject, which I also love, which is a study of not the QCD itself, but its cousin theories, so to say. Namely, theories which possess supersymmetry and are closely related to QCD in that they actually share the same gluon sector. And in particular, as you have probably heard, there exists a so-called maximally supersymmetric n equals 4 super young Mill theory, which has a very good chance to be completely integrable, solvable, and this may help us to get one day the closed answer for deep inelastic dynamics in real QCD just in one line and in all orders. This is, once again, a very challenging program. There has been some development on the way, and I hope one day it will happen. So, my aim is to tell you in a few words what was the story of deep inelastic development from the other side of the iron curtain. So, right after Bjorken came up with his hypothesis, and it has been supported by Slack experiment, it became absolutely clear that Bjorken scaling cannot hold in quantum field theory. And the reason for that is pretty simple. The point is that unlike in an orthodox pattern model where partners were supposed to have finite transverse momenta, in quantum field theory you cannot keep them limited. They can be as large as the hardness of your process. And as a consequence, the number of particles that are involved in your interaction turns out to be large in spite of the fact that the coupling is small, if you want to play this game, if you want to have a quantum field theory with small coupling. So you see there are so-called logarithmic enhancements, which makes probability of producing an additional particle of order 1, which means that you have to resum to take into account all orders in your perturbation theory if you dare to do so. So such collinear enhancements, or in other words, mass singularities, they're typical for all quantum field theories which have dimensional coupling constants, so-called logarithmic field theories. And the physical explanation of this phenomenon is pretty straightforward. It tells you that in quantum field theory, your particle is not a point-like object, as partners, original partners were thought to be. QFT particle is always surrounded by a virtual code of fluctuations. And when you do your deep inelastic measurement, when you increase your momentum transfer, you start probing this code deeper and deeper, and therefore the number of objects you encounter has to depend on the your resolution power, if you wish, on Q squared. So the partner picture was employing the classical probabilistic language. So this is the key formula that the part of deep inelastic, in our case, cross-section involving hadron can be simply written as a convolution of the cross-section of the interaction of your lepton, incoming incident lepton, neutrino or electron or whatever, with the quark, convoluted with the probability of finding quark inside the hadron. So this is the idea of the partner model. And by the way, it is that idea and this which is being practically used when you generate your events using Monte Carlo technique. But now, as long as you deal with quantum field theory, you see, quantum field theory. It's obviously a theory, it deals with fields, but most damaging and important is that it's quantum. And quantum means that there are interferences. You have to, you don't have probabilities a priori, you have to analyze how different quantum states interfere. And so the question arises immediately whether it's possible in principle to talk about probabilistic interpretation, to talk about partners in logarithmic field theory like QCD. And actually, the first answers came before QCD, and the answers, as dialectics tells us, the answer was dubious. It was yes and no. Bjorken scaling, no. It has to be violated logarithmically. Your Bjorken limit doesn't exist. There will be always slow logarithmic dependence on momentum transfer. But at the same time, the answer is yes, because probabilistic language turned out to be possible. And this result was obtained in my institution, close to Leningrad in Gatchina, by these two people, Vladimir Gribov, the leader of our theoretical group, and a young man, Lev Lipatov. since I'm supposed to be a bit historical, let me just tell you the anecdote that for Lev, it wasn't a very happy time because he didn't do very well as a postdoc student, and the elders even discussed whether he should be kept in the department or kicked out. And then in 1969, Gribov was giving a seminar, and that was a tradition that when you did your job, you have to first do a test run on your local theory seminar, in those days in the Yofa institution in Leningrad. And he was giving a seminar describing this work, and Lev started asking questions. And the questions were so nasty that Gribov got stuck and said, Lev, you know, you're already a co-author, please help me. And that's how Lev Lipatov started turning into a great theoretical physicist. So these two guys wrote these two related papers, how to describe deep inelastic in ND plus or minus annihilation in quantum field theory. There was no QCD around, so they've been using two model theories, with one of which looked like QED with abelian field interacting with fermions, and the second with scalar field pseudo-scalar interacting with fermions. Anyway, and they have shown that indeed, having analyzed all the interferences, in the end, you come up with the picture which allows for probabilistic interpretation. And this has been explicitly formulated a couple of years later by Lev Lipatov. There is such a difference in dates because this was original publication in Soviet journal, and this was 72 is the date when the English translation has appeared and became available for the world at large. So we see in Lipatov's paper of 74, there's explicitly the words partner model and in perturbation theory. So then
That's
time
great to
has
see the
come.
background. So,
Yes,
yeah, appreciate that. Sorry.
you have a question?
Oh, no. Just,
No, okay.
yeah.
And then came 1977, and time has come to address the question what's happening in macroscopic theory of strong interaction, QCD. And so these two then young French physicists, one from École Normale, another from Bourse-Rivet, came up with this beautiful paper, Asymptotic Freedom in Partner Language. Simultaneously, some other guy who was also struggling for life, as Lev Lipatov did once upon a time. I was a very bad, unsuccessful PhD student. I wasted 2 years of my, which were allocated for my PhD thesis, because I simply didn't know what to do. And then some smart, clever guy came with the idea, so why don't we give this kid to do the calculation of, in QCD, to do the calculation of things which have been done 6-7 years before by Gribov and Lipatov in model field theories. So that became my project, and that's what I did. And now it is being called DIGLAB for the reason which is written here, citation from Alfred Müller. And in his talk at the Latville conference in 2011, Guido actually showed the historical photo of the preprint where he wrote this equation with his own hand. I must say to the young people that it probably is difficult for you to imagine, but those were days where there were no computers, personal computers, there were no smartphones, no even internet. So you really had to write with your own hand, your formulae, and to draw your pictures and publish, issue what was called preprints. And preprint is something which is really a paper thing, which you would send to your colleagues abroad on their demand. There was an exchange of information, how it looked like some 50 years ago. So this is Guido's handwriting of these famous, excuse me, evolution equations. And the only thing I have to correct here is the number of citations, which has changed by a factor of 2 since his talk in the beginning of the 2010s. So he also showed this picture, which refers to my paper. My paper was submitted 8 days later than Altarelli Parisi. He wrote here that this was contemporary to us meaning Altarelli Parisi, obviously, and to compensate for that too nice picture which Professor Onos has showed you, that was more realistic picture of the author. And obviously these two things were not at all identical. There were a lot of differences between our treatment of the problem. So first of all, I didn't do polarized splittings, as contrary to Guido and Giorgio, who included this thing. At the same time, I did simultaneously plus and minus and deep and elastic, just following the tradition of Gribov and Lipatov. I also discussed analytic continuation through point x equals 1 when the answer becomes singular, just to prove that Drell, Levy, and Yan really had the correct guess that the two processes have to be analytically continuable one into another. So I discussed small and very large X regimes and established relation to BFKL. Strangely enough, BFKL is older than the GLAP. I discussed sigma L as a gluonometer, something which has been rediscovered a year later, because my paper remained completely unnoticed for many years. And also, I looked into internal symmetries between these splitting functions, and in particular, I stumbled upon a strange relation, which I didn't know how to interpret, namely that the sum of the probabilities for a quark to decay into quark or into gluon, so this sum of these first two functions equals exactly the sum of the corresponding decay functions for the gluon into fermions or into two gluons, provided you strip off color factors of your splitting functions. And a couple of years later, it was realized that this is not an accident. It's actually the consequence of supersymmetry, not of the QCD itself, but as I said already, of a cousin theory, which is pretty close to QCD, but differs by meta content. And all the fields there, be it scalars, fermions, and gluons, they have the same color properties. So there is no color factors entering the game. And to the best,
appreciate the background on that. I do want to make sure I give you time to make some concluding remarks if you would like. So go ahead with that.
Excuse me, I can't hear you.
Oh, yeah, no, if you want to go ahead and make some concluding remarks, go ahead.
So since I showed you Guido's handwriting, let me show you also mine. So this is how real preprint look like. Now this is one of the pictures. So you see, I have published this preprint after I have submitted the paper, because it took me some time to translate it into what I thought was English. So I submitted my paper, and the editor insisted that I have to explain it in more detail, because it was too long and too heavy, if you wish. So I had to do that. It took some time, but as a result, the paper exceeded by factor 2 the limit which was allowed for publication is in a Journal of Experimental Theoretical Physics. Nevertheless, the paper was published, and the editor was actually reprimanded when his chief returned from vacation. And the picture, which belongs to the preprint, but which doesn't belong to the publication, is this. It's the Gauss diagram, where I try to show what is our domain of ignorance about strong interactions. So these little things we can control, the case of quarks and gluons, at small distances, but we don't know neither how the initial state is organized, nor what is happening in the final state. All these things together make this nice lopsided hot dog, which looks like a ghost. So Guido contributed to many pressing issues of high-energy particle physics, not only QCD patterns, but also he was involved in high-order QCD studies, and in particular with special stress on transverse momentum distributions in hard interactions, like Drell-Yan process. He was instrumental in developing the strategy of weak boson discoveries. In developing the theory of leptonic decays of heavy quarks, and in particular in neutrino mixing. But what I think is more important is that at his position at CERN, he actually has become what I would say maman poulet for the whole community. He was a keeper of the standard model and the beyond standard model physics. And it was not only sort of watching out what is happening, but he was also promoting ideas. He was taking care of young people, newcomers in the field. And so really his place in this respect was completely unique and appreciated a lot. So he kept all this thing in this head, and to give the best appraising of the role of this man in the history of our field, I would use the words which my teacher used to say to express appreciation or even admiration to someone. He would say, "This person, he has a picture." To have a picture was the best possible praise in words of Professor Glebov. And Guido was one of those people. So my congratulations to the winners of the Altarelli 2025 award. And I'm sure Guido would have been happy to see you here. And you have every reason to be proud of this most distinguished recognition. Thank you.
Thank you very much. So I'd like to move on to the presentation of the awards now, and thank you again, Professor Dokshitzer, for joining us. And if you look in the webpage, this is actually the 10th year that we've given the award. So it's quite a history. And I think if you look over the past recipients, they've gone on to do some very significant contributions to our field. And we expect these current award winners will do the same. So great. Yeah, we should just do, yeah. Share in full screen. To move on to the presentation of the awards now, and thank you again, Professor Dokshitzer, for joining us. And if you look in the webpage, this is actually the 10th year that we've given the award. So it's quite a history. And I think if you look over the past recipients, they've gone on to do some very significant contributions to our field. And we expect these current award winners will do the same. So great. Yeah, we should just do, yeah. Share in full screen. Is it? Okay. Yeah, thank you. Okay. All right. Yeah, so you can see the list of winners on the screen there. Thank you. And again, thank you to our sponsors. Thank you to the members of the committee that did the selection. It was a very difficult choice. We had many, many good candidates. That's always a challenge. But our first awardee on the experimental side is Miguel Arratia. And you can see his brief bio here. So it's a pleasure to have him. And so their certificate for the 2025 award recognizes him for advancing jet studies in deep inelastic scattering and developing high granularity calorimetry for the electron-ion collider. And then the awardee for theory goes to Rene Poncelet, and his vita is up there. And the citation reads, for outstanding contributions to precision calculations of the top quark and Higgs bosons, which have profoundly influenced OHC analyses. And so now what we'd like to do, we'll do pictures at the end during the coffee break, but we're just going to have a brief presentation from the two awardees, and we'll start with Miguel first. So we'll go on, and if I could have Miguel come on up. Yes. Congratulations, and I'll turn it over to you.
Okay. Hello, I'm deeply honored. Thank you very much. Thank you very much to the committee. You're far too kind. Today, I will present briefly some work on jets, what I call jets in deep inelastic scattering 2.0. I will try to describe what I mean by that. So the overview of my talk is very simple. It has three parts. In the first part, I will describe jets in deep inelastic scattering, what I call the 2.0. Then I will pass into jets but at lower energies, at fixed target energies, where we can do studies of nuclear effects in semi-inclusive deep inelastic scattering. And the third part of my talk will be in the EAC realm. So why do I say jet physics in deep inelastic scattering 2.0? I really think that we are entering a new era of jet physics. And this was triggered by a few groups that proposed completely different uses of jets as tools that are different from what was already measured at HERA. Of course, jets in deep inelastic scattering were studied extensively at HERA, but with the advent of the EAC, people reimagined what you could do with jets. And in particular, these two groups proposed to use jets to study TMDs, like transverse momentum dependent PDFs, and effects and the evolution of those that allows us to extend the work of Big Lab authors into the TMD evolution. Those two groups proposed to use actually the Born level configuration. This is when you have one jet in the event that is recoiling against the electron. If you measure that precisely, then you are getting access to TMDs. So this is completely the opposite of what used to be the case in HERA, where the higher order processes that were sensitive to gluons were the main event. The leading order jet configuration was considered a background, literally called a naive quantum model background in HERA measurements. So this is the complete opposite of the typical proverb that we heard here in particle physics, that yesterday's discoveries is tomorrow's background. This is the opposite. And in that context, during the same time, 2019, we had the opportunity for the EAC Yellow Report to rethink what we will be able to do with jets at the electron-ion collider. Before EAC Yellow Report, there were very few mentions at all of jets in the EAC context or papers. That has changed. There was a time where we had lots of fun imagining what future measurements would look like, doing projections, experimental projections, and phenomenology, proposing new observables. I will not go into all what you can do with jets, which are really core to the old EAC science, including TMD, spin, and cold QCD. I will just give you two examples. With jets, we will be able to study transverse spin effects, TMD effects, like jet sievers. That's the plot you see on the left, where the error bars in theory and the error bars in the data is what we will be able to measure, we think. With simulations, we convince ourselves that we can sample this distribution with the beams that are shown here. And on the right-hand side, you see a new type of observable that we proposed called a hadron in jet Cummins effect. So this is basically a jet fragmentation study where you induce a spin asymmetry that changes the jet fragmentation. So those are just two examples. But as I said before, jets are really now considered to be a core tool. And during that period of time where we imagined the future of jets, many groups did many studies that I will not do justice today. But simulations can only lead you so far. So I had the heretical idea of measuring some of these new observables, but with old archived data from H1 at HEDA. That turned out to be a success, despite that it was a little bit of a gamble. The first measurement we performed, this was published in 2022 in a PRL, we measured the lepton jet imbalance, what you see on the left event display, basically. And so we measured the Q value, Q vector, which is the imbalance between the lepton and the jet, and the spectra shown here in the data, compared with two calculations. One of them, in the blue, is a TMD calculation that describes the data at low values of Q, and at high values of Q, we describe it with PQCD. What is interesting and what was never observed before is that there is a period or a range in Q where both the TMD and the PQCD calculation describes the data. That's the so-called matching that we absolutely need and people were certain for, but it was not observed in deep inelastic scattering before. If you try to do this in lower energy deep inelastic scattering, it just doesn't work out. So that's just one example that improves. Sorry, Professor, I'm going to move you because I need to show here that we did this measurement with EAC in mind. So all the kinematics, the jet PT, the Q squared overlaps with EAC. So we convinced ourselves that we can do these measurements now. If we repeat the same measurement, but now we have polarization with EAC, we will be able to do exactly what I showed you before. So this is very promising and improves that both the theory and the experimental aspects are very sharpened. That's just one example. The H1 jet measurements are evolving into a jet program. Many results that I will not do justice today. Okay, let me. One aspect that we learned very quickly, though, is that if you want to do TMD studies in the bright frame, as one of the groups that I showed you before suggests, we really need a new jet algorithm. The almighty, the powerful, the famous anti-KT algorithm fails completely. The reason for that, we realized very quickly. If you go to the bright frame and you want to study the Born level configuration, you have a jet going to infinity in rapidity. So if you run your anti-KT algorithm, it will break that jet into 1,000 pieces. So we need a new jet algorithm. We proposed one. I call that the Centauro jet algorithm. This is the first asymmetric cluster metric ever. And we did that in order to be able to cluster the struck quark jet. So we can do that, unlike the KT algorithm, but we kept all the good properties of KT and the KT family, like the longitudinal invariance and the fact that it avoids clustering with beam remnant. So this new jet metric has been used already in various event shape studies. And there are even competitors. We will see, time will tell which algorithm is the new anti-KT. But for now, I will show you for the first time the first measurement. For this esteemed audience, we prepared a new result, which is the first measurement of the Centauro jet spectra. This is a preliminary result from the H1 collaboration. On the left-hand side, you see the PT spectrum. That looks interesting in the sense that it's a PT spectrum that peaks at around 1 GeV, and it has a fall-off at low PT. This is what we are expecting. This is a TMD effect. We're probing TMDs. So you expect like a Gaussian-like curve at low PT. Or in other language, you expect this from resonation effects. And on the right-hand side, you see the energy fraction of these jets that peaks at around unity, which is what we expect. Most of the energy is carried by the struck quark jet. So this is the first, but it will not be the last measurement and studies of jets in the drive fan. Now I will pass my second part of my talk on electron nuclear scattering and class at Jefferson Lab. This is also jet physics. We study jet fragmentation, correlations, cold QCD, and spin effects. Although, of course, it's not literally jets reconstruction, but we measured hadrons, single and double hadron production. And I will summarize what we have learned about this new program. So one of the things that we measured was the TMD fragmentation of charged ions in nuclei. So relative to a light nuclei like deuterium, we observed that the TMD fragmentation function is dramatically changed, and the data you can see in there. The ratio is not unity, and it's far from unity. This data can be used and has been used to get TMD PDFs that are nuclear, the fits doing that, or fits of nuclear fragmentation functions, or electron nucleus Monte Carlo tuning. We went beyond that measurement, though, because that type of measurement had been done before. But we did a measurement that no one had done before in electron nucleus scattering, which are dihadron correlations. So what is that? You have two hadrons, and you look at the azimuth dependence of their production and how that changes between deuterium and heavy nuclei. And what we discovered is that this correlation function is dramatically changed. You can see here, red is shown in the baseline deuterium. The moment you go to carbon, iron, and lead, this distribution gets significantly broader. We don't really understand that fully. Might have to do with change in nuclear TMDs, we will see. But in any case, this is a crucial reference for future measurements, because we really plan to do this exact same measurement at exactly the same Q squared, but at lower X at the electron ion collider. So the next chapter in this CDS program at Jefferson Lab is very, very exciting. We have a new experiment that took data just last year with higher energy, and we are going to throw a spin to it just to see, to destroy theories, as Professor Abe was describing before. And we are going to have a new experiment which is going to use polarized lithium-7 and polarized electrons, and that's coming very soon. So we will extend these two particle correlations to the spin Brown too. Last but not least, I will describe EPIC, my work in EPIC. This is the EPIC, beautiful EPIC detector. You see the 3D models on the left-hand side, an event display on the right-hand side. The EAC is going to be a jet factory, and it will produce the first jets in polarized DIS with the polarized proton, and the first jets in electron nucleus scattering. So it will be very exciting, and I will, in order to make the best measurements we can of jets, we need the best detectors, state-of-the-art detectors. And so I will present some of the work that my group has done. This is my brainchild, the calorimeter insert. This is a sampling calorimeter that is located at the heart of the forward hadronic calorimeter. So it covers rapidity between 3 and 4, and is high granularity using the SciPM on tile technology. That is a technology that is very hot in particle physics, but it was not really mentioned or thought about in EAC context. For just to give you a context, it was not included in any of the detector proposals or included in any R&D. So it was a hard sell. Even though this is a small detector, we had to work hard to persuade our collaborators to include this. And I'm very grateful that this is now part of the EPIC detector. This will be able to measure the jets that are the highest energies at the EAC, as you can see in the jet spectra on this plot, up to 200 GeV or so. And in order to fully exploit the capabilities of the detector, we developed software and reconstruction code and methods that are really going to exploit all of this. So beyond the insert, which is, as I said, part of EPIC, we use the same concepts to propose, oops, there's something wrong in this image, but to propose two other detectors, which are very crucial, both small, but play a very crucial role in EPIC. One of them is a 0-degree calorimeter, and the high granularity and all the methods and design choices that we made for insert really help the physics of the ZDC, which has to measure neutrons, lambdas with very high angular resolution, and photons too. So that's also part of EPIC. Now, what is not yet part of EPIC, but is a concept that we proposed, is called FDC, few degree calorimeter. And that would be a calorimeter that would be located behind the crystal calorimeter in the backpack region in EPIC. And the purpose of this detector would be to cover that pseudo-rapidity range that's crucial for the discovery and study of gluon saturation at the EAC. So with that, I will finish. I will thank all my team at UC Riverside, all my collaborators, which are way too many to list, and also sponsors. So thank you very much.
Hey, thank you, Miguel. Now I'll call on Rene. Again, there's his citation. And without further ado, on your presentation.
Hello, everyone. I'm, of course, it's an absolute pleasure for me and an honor to stand here and receiving this reward and giving now a small presentation about my research. The next few minutes, I would like to tell you a bit about precision predictions for hadron collider physics, which is a subject probably sounds a bit dry and technical to many of you. But I hope I construct a story which makes it sounding very interesting and also show that it's actually of great value for particle physics in general. So the story really starts at the heart. So we all, in some way or another, studying inelastic scheduling processes. And we do so to understand the fundamental objects and the actions of nature. And we do this typically by measuring scheduling processes and comparing these to theory predictions. Right? If these predictions, the measurements agree, we of course see that we can constrain parameters of our model. If not, we have to incorporate new phenomena into the model. And this is really what the cycle of measurement and theory, which really led us to the development of the standard model of particle physics. And the discovery of the Higgs boson really nicely confirmed our current model, which we have. I want to focus here on one specific aspect of this, and this is the word agreement. And I think agreement here really is important to mean by this, that the data and the theory agree within their uncertainties. And in turn, this of course means that whatever we do, whatever we extract from measurements, will be limited by our knowledge of our uncertainty and the precision. And this is, from a theoretical point of view, this really means that we have to work hard to make precise predictions. This gets even more transparent if you're moving on to the future, having more and more precise measurements. For example, the high luminosity at HG will do many measurements with unprecedented precision. I took you just one random example, which is the projection of Higgs coupling measurements. I took this because it really nicely shows that there are cases if they're really limited by the theory uncertainty, which we can see here. If you look at the breakdown of uncertainty in the red bar, you see that the theory dominates for many of the decay channels. Getting good theory for the future means two things for me. One thing is that we, of course, need accurate predictions, right? We want to avoid to wrongly interpret excesses over data. And on the other hand, we want to have precise predictions because we have to be getting some data and we want to get the most out of it. The more precise, the better we have make use of this. And my tie-in of Altarelli here is that this, I think it's really a pillar of what we do these days, in the sense that it's really the starting point of precision calculations for hadron colliders. You all know, of course, the DIS equation that describes the evolution of the proton PDF or other PDFs with the energy you're probing them at. And in the way, when you're solving these equations, you nicely reach some large logarithm rising colony emissions, leading to a more stable prediction. But also, it allows you to correlate different processes at different energies, which gives you essentially the possibility to constrain PDF. This sounds kind of trivial because we all do this, we all know this. But I just want to recap essentially that this is really the basis of any precision computation we do at hadron colliders today. I will look now a bit on LHC physics because this is what I was mainly working on. So, for example, if you write hard-on cross sections in collinear factorizations, you typically write them as a convolution of apparent distribution functions, or evolution with the energy, as I described before, is governed by the D-Club equation with the Platonic cross section. I'm really working on this Platonic part here, which is a part which we can actually compute in perturbation theory. If you, for example, looking at fixed order perturbation theory, expansion would look like, for example, here you get a leading order next to leading order contribution. This increasing powers of the strong coupling in this case. If you're looking at the uncertainties of these expansions, we can quite nicely estimate just from the size of the coupling that we're essentially getting an order of magnitude uncertainty for the leading order, a 10% uncertainty for the next leading order, and about 1% uncertainties for the next leading order. Actually, they're quite high, slightly bit higher, but this is roughly just from the parametric dependence. And it's clear that if you have very precise measurements, if you're talking about percent level precision measurements as LHC, you really need this next to leading order calculations. And even more, in some cases, we need in QPLO and beyond to actually do this. So in the next couple of minutes, I would like to highlight three examples which I encountered during my research on this subject. Where I really think that higher order QCD calculations really matter and make a difference in how we interpret and see the data. The first one is also one of my earlier works, which is really about top quark physics. So this is about top quark pair production, and this is a process which is, of course, greatly studied at the LHC. There are many things you can study, but among those, there is the process of there's an observable which is connected to the spin of the top quarks. The different ways to construct it, but one specific way is this delta phi distribution, which I showed you on the left-hand side, which essentially is essentially the asymptotic difference between the two leptons in the dilepton channel for the top quark production decay. What you can see for this observable is a comparison with respect to next to leading order QCD and next to leading order QCD. In black, you see Atlas data. What you can observe is that there's a distinct shape difference. And if you work at next to leading order QCD, this shape difference is really not distinguishable, essentially, from new physics effects. Only if you go to next to leading order QCD, you really see that this is actually a standard model effect. So this is a clear sign that what you need is that this higher order prediction really change the way you interpret the specific set of data. These kind of corrections not only is relevant for the specific observable, for example, spin density matrix elements receive similar corrections. So whenever you use something like the spin density matrix to interpret something, you have to keep in mind, even though these are kind of bond-level quantities, that they come with intrinsic QCD corrections. The second thing, the second example I would like to bring is an example where we need higher order calculations to make the theory itself internally consistent. And this is now centered around the production of fixed bosons in fluid fusion, which is the most dominant channel at the PP collider, which of course therefore received also a lot of attention of the theoretical community to make precise predictions. We're talking about NQ predictions for these kind of processes in the effective field theory approach, where we shrink the top quark loop, which mediates the interaction between gluons and the Higgs boson to a point. So these are very, very precise and very, very serious, very, very tough computable predictions to compute, but still there are still remaining uncertainties here. There are many different things. There's a breakdown here shown, but due to the short time, we will just focus on one specific contribution, which is the effect of top quark masses or quark masses in this process. So the reason for this is a contribution which we can nicely tackle with perturbative methods and try to estimate the effect of this. This inclusion of the quark masses here really makes this computation much more difficult. And so we cannot go out to NQ, but we can do it at next to leading order. And we managed recently to incorporate also all the quark mass effects in these. And focusing on one specific contribution, which is the interference, for example, between different quark masses, top and bottom here, we can see that next to leading order calculations are actually necessary to properly understand these effects. For example, there are intrinsic different methods how we treat these quark mass effects, and they will lead to very different results. And only if you go up to next to next in order, you get a consistent result of this correction and can estimate properly that certainty. The last example I would like to show is an example from jet physics. So we're looking now at multi-jet events, and we're looking at one specific observable, which is called the transverse energy correlate. This is essentially similar to the TD bar case, an azimuthal observable, but now weighted with the energy of the jets. And this observable has a couple of nice properties. In particular, it allows us to separate certain soft and collinear regions, but also it has a very strong dependence on the strong clumping constant. And this is experimentally very nice, we can measure this due to the high statistics at very, very high energy quite precisely. Additionally, this is also an observable which can very precisely compute the perturbation theory. This is essentially shown here. So we have here again an atlas measurement. If we compare next to leading order QCD, blue and red, next to order QCD to an atlas measurement of precisely this quantity for a range of different energy scales. What you can observe is that you really, really gain from doing these next order QCD computations in terms of reduction of uncertainty, but also how the shape of this distribution look like. The impact on the actual measurement can be best gauged if you're looking at the extraction of the strong clumping constant from precisely this observable. And this is shown here. The left-hand side, the extraction is shown at next to leading order QCD, while the right-hand side, next to leading order QCD. You really see the difference in the yellow band, which really shows the uncertainty of these measurements. It's the same data, but different theory predictions. And this is really what the sprint is about. So I didn't talk about any of the technical details that go into this. So there are many, many aspects which we have to get under control, starting from loop amplitude, subtraction schemes, numeric integration, if needed, even resummation and fragmentation, putting everything together in into one big higher order computation. These higher order computations will take a long, long time. And it's always really, really scary if you then finally put everything together and run the numbers. And it's always like a super excitement if you then finally unveil everything and looking at these plots. And that's really the fun of this game is you don't know what the correction will be, but if you see then that it really improves on things and brings pieces together, then it's really, really exciting. And eventually, this has an impact on the interpretation of data, which is really what we want to have. Yeah, with this I would like to conclude. So I hope I convinced you that the predictions predictions are essential for data interpretation, and we need them really accurate and precise, and getting back this most of our work. And actually, QCD calculations, which are most important for these hadron colliders, went a very long way from the 70s to today. And many, many milestones have been reached in this step, but there's still many challenges ahead. And I think the most challenging thing for the next decade is really the full automation of this next order QCD calculation and the incorporation in full-fledged Monte Carlo simulations. Yeah, but there's a lot of work to do, and I think there's a lot of free space for novel ideas in this field, and also a lot of space for surprises. So this is very exciting. Okay, I would of course close with thanking all my collaborators, in particular my mentors, Michal Chakon and Alexander Mitov. Without them and their guidance, I wouldn't be here, of course. Thank you very much.